All right, in this video, I'm going to be doing an overview of solving systems of equations and inequalities algebraically. So this is kind of a recap of both 4.2 and 4.3, just using algebraic methods to solve a system, okay? So with question number 1, I'm going to be using the substitution method, and with question number 2, I'm going to be using the addition method, okay? All right, now, the way the system looks on problem number 1 is the type that is best solved by using the substitution method. The kind where one of the variables is already by itself, then you really should use the substitution method. It'll be a little bit easier. So x is already by itself on that second equation. Circle the x in that top equation. We don't know what these look like, but we're kind of assuming they do that, and we're looking, remember, for that point of intersection. So at this point right here, we know the x from one equation and the x from the other would be equal. We also know the equal sign on that second equation means that 4y minus 7 and x are equal to each other. So I can replace or substitute for the x in that first equation. So where there used to be an x in that top equation, I'm going to wind up putting the 4y minus 7. Now everything else still needs to be there. So all I did was right here where there used to be an x, right? It used to be 2x plus 3y equals negative 3. So where the x used to be, I'm putting the 4y minus 7. Now at this point right here, I'm now back to a chapter 2 type situation. So I'm going to distribute the 2. I'd get 8y minus 14 plus 3y equals negative 3. These like terms are on the same side of the equal sign, so I just combine them and get 11y. And then from here, I'm going to finish solving that equation by adding 14, which gives me an 11 on the right and an 11y on the left. And then I'm going to divide by 11 on both sides to get y equals 1. Okay. Now, what the y equal 1 really is the horizontal line through that point of intersection. So at that point, we know the y coordinate is 1. We need to get the x coordinate. So what we're going to do is take that equation. It works best to take the one where the x is already by itself and then go plug in to that equation. Right there where the y is, you can put a 1 because you just found out y has to be 1. So put a 1 where the y is and work that out, and we wind up with the x being a negative 3. So x being negative 3 like that is really telling me that the vertical line through that point of intersection, okay, would be x equals negative 3, just like the y equal 1 really meant the horizontal line, y equal 1 goes through the point of intersection. So since y equaled 1, we know the y coordinate's 1, now we know the x coordinate is a negative 3. Okay. Now in ALEX, they just do the x equals and the y equals. Just make sure you put them in the right spot. Even though we found the 1 first, it's an x, so make sure you put it in there for x. Okay. Now, with question number 2, the way the x and the y, they're on the same side of the equal sign. With that type, it works best to use the addition method. So what you would do is you would decide which variable you're going to try to eliminate. Sometimes there's a real advantage to working with one versus the other. With this one, it really wouldn't matter. I think most people do best if they just concentrate on getting rid of the x variable. We'll see how there's a 2 in front of the x on the top equation and a 5 on the bottom. the least common multiple of those two numbers would be 10. So what I could do is do 5 all the way through on the top equation. And then down here on the bottom one, if I did a 2, that would get me to a 10. But I'm noticing that this would be 10x. I need this to be negative 10x. So I'm going to multiply by a negative 2. Okay? So whether you need the negative kind of depends on how the original equations looked, whether there was already a negative there. So I'm going to go ahead then and multiply through by 5 on that top equation. Don't forget to multiply every term by 5, including the right-hand side, so that you're not, see, that way I'm not really changing the original system. So it may look something like this. When I multiply through by 5, let's say this was the first equation, it would still look like that same set of ordered pairs. I'm going to multiply the bottom equation through by negative 2. So that's going to be a negative 10x, but then a negative times a negative would be positive 8y, and negative times a negative would be positive 26 on that right-hand side. So again, that second equation hasn't changed. Multiplying everything by negative 2 doesn't change the set of ordered pairs. But now something's going to change. Now I have the 10x and the negative 10x are opposites. And so what I'm going to do is add the two equations, and I'm going to combine the like terms. So 10x and negative 10x, they're opposites. They cancel out. You would get 0. 25 and 8 would be 33y. And over on the right-hand side, 40 and 26 would be 66. So at that point right there, I have an equation that just has a y in it. So it's going to be a horizontal line. And I can divide by 33 to get that the horizontal line would be y equals 2. So this is y equals 2 right here. And that means I know the point of intersection has a 2 in the y spot. Now I need to find my x. So I'm just going to go to one of the equations. A lot of times I'll go to the one on the bottom. I'll go over here. And just where the y is, I'll put in a 2. But you might have picked the top one since it didn't have any negatives. But it really doesn't matter that much. Okay, so 5x minus 8 would be negative 13. So when I add 8, I get 5x equals negative 5. And when I divide by 5, x turns out to be a negative 1. All right? And so that means I've now found the vertical line right here. Oops, supposed to go through, trying to make it go through that point of intersection. That vertical line right through that point of intersection. Okay? And the vertical line has the equation x equals negative 1, so I now know the point of intersection should be negative 1, 2. So where x is, you put negative 1. Where the y is, you put the 2. Now, let me comment on the fact that you can check these. All right? So you can do a quick check by just doing this. I used, on question number 1, I used the x equal 4y minus 7 to find my second coordinate. So for my check on that one, I would use the other equation, and I would plug in the 1 for y, the negative 3 for x, and I would check to make sure that it gives me what it's supposed to. And sure enough, it does. Negative 6 plus 3 does equal negative 3. So I know I'm right. You would do the same thing on question number 2. So I found out that y was 2, and then I plugged it in, and when I plugged it in, I plugged it into the bottom equation and found out and made it tell me what the x would need to be. So your check on that one could be done by taking the other equation, the one you did not yet use, and then plug in for the x and the y and see if you get 8. So plug in the 2 for the y, the negative 1 for the x, and double check that that works. And there's negative 2 plus 10, which does equal 8. So I know that on this one, the point of intersection is negative 1, 2 for sure. And on this one, the point of intersection was negative 3, 1 for sure. Okay, so if you got a little extra time, be sure to do those checks. So in this video, I'm just doing the overview of solving algebraically. All right, on this one, I'm going to solve it using both methods. So if I were going to solve using substitution on this one, it would work okay. It would work pretty well, because I would take that y and I would notice that that y has an understood negative 1 in front of it. So I could take that equation and work on getting that y by itself. So this one's a little different because, see, on this one of the variables was already by itself. On this one of them wouldn't be too bad to get by itself, so I'm going to work on that. So if I want to get the y by itself, I needed to subtract that 3x from both sides, since it was positive. Okay. Then I needed to get rid of the negative 1, the understood negative 1 in front of that y. And so that equation becomes y equals 3x minus 7. So that's the same as that first equation. Now, if I'm using the substitution method, what I'm going to do is replace the y in that second equation by this. Let me write, here's our new first equation, and then here's our second equation. Let me just get it where it's near where I'm trying to work. So at the point of intersection, those y's are the same, so I can replace the y in the second equation by the 3x minus 7. But everything else on that second equation still needs to be there. Just the y got replaced with 3x minus 7. So for this one, you would distribute the negative 2. Okay, so distribute that negative 2. Then combine your like terms. These two combine. And then keep working until you get that x by itself. So you'd have to subtract the 14. So you'd have your negative x, negative 1x equals negative 14. And now we can divide by negative 1, top and bottom. So x would be 4. Okay. You would still need to find the y, and this would be the best place to plug in to get it. So we know that y should equal 3 times whatever x is minus 7. So we'll put the 4 right there, and that tells us the 4 right there. Then that tells us that the y would be 12 minus 7, or 5. So y should be 5. And x was here. X was 4. And so to check it, I would use this equation and put in the 4 for x, put in the 5 for y, and see if you get 10. So 20 minus 10, 20 minus 10 does equal 10. So it checks. All right, that's the substitution approach. Okay. Let's do this same problem, but let's do it using the addition method. If you're using the addition method, you want to add the equations together, but you can't add them right off the bat. In most cases, you need to get it to where when you add, one of the variables will go away. So I'm going to notice that I have a 3 and a 5. So I could multiply the top equation by 5 and the bottom equation by 3. But if I did that, I'd have a 15 and a 15. So I need that bottom equation, or one of the equations, to have a negative on it. Then multiply through by the numbers that you now know are going to do what you need. So 15x minus 5y, 35. Negative 15x plus 6y equals negative 30. Don't forget to multiply both sides all the way through. All right, now we did what we did right here so that these terms would be opposites, so they'd cancel out, and we wind up with 1y equaling 5. Notice that's, of course, the same as what we had before. And then we just need to plug that 5 in somewhere. So 5x minus 2 times 5 should equal 10. So 5x minus 10 should equal 10. And then we can just add the 10. We're just solving now for x. That gives us 5x equals 20. And then when we divide by 5, we get x equals 4. So that's how it would look if I had solved that question using the addition method. I want you to know both, but if it says to solve using a particular method, it doesn't really matter which one, as long as you use an algebraic technique. Okay? So for substitution, I'd be looking for this step right here. This is the key that shows me a substitution approach. For the addition approach, I'm looking for something like this. And then you're not going to get any credit for a problem if all you're really doing is guessing and checking to get the answer. So make sure you know how to do substitution for cases like this one for sure. And then the addition method works well on ones where the x's and y's are on the same side. And making this happen right here is the key to the addition method. And replacing one of the variables is the idea behind the substitution method.